And so basically, there was a lot of experimental data on energy emitted from the, from excited hydrogen atoms in a gas. And what Niels Bohr did is he imagined the nucleus of the atom as, having the positive charge and being at the center, and the electron just going around it, right, in a circular path. So first of all, the electron doesn't go around in a circular path. And Niels Bohr came up with this model in 1913, and that was a result of an experiment and studies that had been done by Ernest Rutherford in 1911, 2 years earlier. So 2 years before Niels Bohr, Rutherford discovered that an atom has all of its positive charge and most of its mass at the center in a very, very small volume. That most of the atom is empty space, and that the positive charge was at the center, which later on became associated with the nucleus of the atom, and that the electrons were outside that, right? So they were outside. What they were doing outside, who knows? But they were, at the center of the atom, there was a positive charge. That's where the positive charge was. And then Niels Bohr came along 2 years later, and he said, well, what if you discovered that the protons, the positive charges, are at the center, right, and that the electrons are outside? So Niels Bohr just said, what if these electrons orbit around the nucleus of the atom, very much like planets orbiting around the sun? And he just took the easy path. He said, what if we consider a perfectly circular orbit, right? And then solve that problem, right? Think of an electron. Well, we learned that they are not in the nucleus, they're outside the nucleus, so let's just think of the electrons as going around in a circular orbit around the nucleus. In the case of an atom, right, of a hydrogen atom, that nucleus would consist of one proton, at least for the most abundant isotope of hydrogen. There is another isotope of hydrogen where you have one proton and one neutron. It's called deuterium. And there is another less abundant isotope of hydrogen with one proton and two neutrons. It's called tritium. But the most abundant isotope of hydrogen has one proton. In fact, the proton is the nucleus of the hydrogen atom, and one electron going around it. So he just imagined an electron going around the nucleus, right, going around the proton, and the only force of interaction between that electron, that one electron, and that one proton is just an electrical force. An electrical force of attraction. The electron is negatively charged, the proton is positively charged, they attract one another, and because it is an attractive force, right, then that force acting on the electron is directed towards the center of the circular path, so it is in the centripetal direction. So, in the model, I'll show you what is considered, and then what Niels Bohr successfully did was he was able to come up with a mathematical expression for the total energy of the electron. So let me go through that. And so there's a little bit of algebra involved, but so we have this. So this is the Bohr theory of the hydrogen atom. A more accurate theory is using quantum mechanics, which was developed in the, this was like one of the precursors, but it was developed mostly finished in the 1920s. But quantum mechanics, if we use that theory to solve the hydrogen atom problem, then we'll see where Niels Bohr went wrong and what the corrections are. But the problem with that theory using quantum mechanics is that you have to solve the second order partial differential equations. And so in this class, we're not quite ready to do that. So, at least I'll discuss the simplest case. I'll say where Niels Bohr went wrong and where he went right. So he considered the proton at rest, at the, making up the nucleus of the atom, and the electrical charge of the proton is plus E. So E is 1.6 times 10 to the minus 19 coulombs. It's the charge of an electron, charge of a proton. A proton and an electron have exactly the same charge, same magnitude of charge, except that one of them is positive, the other one is negative. So it's just, so E is 1.6 times 10, 1.602, I think, but 1.6 times 10 to the minus 19, and the unit of charge in the metric system is the coulomb. So 1.6 times 10 to the minus 19 coulombs. And I'll just say, I'll use the symbol Q to represent the electric charge. And then we have an electron over here of mass m, and it's orbiting around the nucleus, which is positively charged, right? So this is negatively charged, and it's orbiting in a circular path. Right? And the charge of this particle, the mass is m, and the charge of the electron is, I'm going to call it Q2, which is minus 1.6 times 10 to the minus 19 coulombs. I'm going to use E to represent the magnitude of the electron charge, or the magnitude of the proton charge. Those of you who have taken Physics 280, you're familiar with the letter Q being used to represent electric charge, right? We use mass to represent, we use M to represent mass, and we use Q to represent charge, electric charge. And these two particles, the proton and the electron, actually they exert two forces on one another. One of them is a gravitational force, because both of them have mass, but that's much too small, it's feeble, it's much too weak compared to the electrical force, so we are just going to consider the electrical force of attraction between the proton and the electron, right? And Niels Bohr thought of the electron as orbiting at a distance r from the proton. All right. So the first thing that he wrote was this: the sum of the centripetal component of the forces on the electron is equal to the mass of the electron times the centripetal component of the acceleration of the electron. So that's the mass of the orbiting particle, which is the electron, right? So that's, sometimes people call it m sub e, but I don't want to write e so much. I'll just call it little m. I'll call this one maybe m big M, right? And the only force acting on the electron is the electrical force, and it is directed towards the center. It is along the centripetal axis, towards the center. So you can think of a centripetal axis, like you did in Phys 185. And so that force, the nice thing about it is that because it is an attractive force, it is directed straight towards the proton. So you don't have an angle like a theta. So you don't have to say F cosine theta, F sine theta. It's just the force is directed along the centripetal axis. So it is just the magnitude of that electrical force. I'll just write it like that. And that's the mass of the electron. And then the centripetal acceleration of the particle is the speed squared divided by the radius of the circular orbit. Now, you learned in Physics 185 that if an object has mass m1 and another one has mass m2, and they're separated by a distance r, that these two objects exert gravitational forces on one another. And both of these forces have the same magnitude. And Newton wrote, when was that? 1687. He wrote that the magnitude of that gravitational force, just the magnitude of it, is some constant multiplied by the two masses and divided by the square of the distance between them. And you learned in Physics 280, and I realize many of you haven't had a course in Physics 280, but you know, it's very simple. There was a guy by the name of Coulomb, whose last name is used as the unit of charge in the metric system. Charge is a scalar quantity, but if you have a charged particle with charge Q1 and another charged particle with charge Q2, and they are separated by a distance r away, these particles can either attract one another or they can repel one another. by way of a different kind of force called the electrical force. And the mass of a particle can only be either 0 or positive. Right? Photons have 0 mass, but if it has a mass, it's going to be a positive number, never a negative mass, as far as we know. So because the algebraic sign of mass is only 1, can only be positive, then the direction of that gravitational force is only attractive, and that's it. In the case of the charged particles, right, the charged particles, we know that they can be positive, both of them can be positive, or both of them can be negative, or both of them can be, or one of them can be positive, the other one is negative. And what we remember is that if the charges are opposite, they end up attracting. So if this is plus, this is minus, they end up attracting. So, and that's an electric force. And it's the same magnitude as the force felt by the other one. And Coulomb wrote in the 1800s, I don't know exactly when, but he wrote that the magnitude of that electric force is, well, a different constant from that. It's called Coulomb's constant. And then you multiply, in this case, the two masses, but here you multiply the two charges. And then you divide by the distance squared between them. So this is known as Coulomb's constant. And it's equal to 9 times 10 to the 9th. And the units would be what? Newtons, meter squared, divided by Coulomb squared. And Coulomb's constant can also be written as, in terms of another parameter, which is 1 over 4 pi epsilon naught. This guy here is called the electric permittivity of free space, of vacuum or free space. And if you make Coulomb's constant equals to 9 times 10 to the 9th, then epsilon naught comes out to whatever, it'll be 1 divided by 4 divided by pi divided by 9 times 10 to the 9th, and you get that epsilon naught. It's just a parameter having to do with electrical properties of vacuum. What is it? 8.85, I believe, times 10 to the minus 12. And they would have the inverse units of this. Anyway, so the magnitude of the electrical force, right, is equal to Coulomb's constant times the product of the two charges. Now, I'm going to write them both like this, both positive, because I want the magnitude of the force, right? The fact that one of these is positive and the other one is negative tells me that they attract. So I already took the signs, the algebraic signs of the charges into account by drawing this electrical force as an attractive force exerted on the electron by the proton. So this is plus, that's negative, right? And so what I want to be here is the component of that centripetal force, which is towards the center. So that is positive. So I want a positive number over here. If I put in a minus sign and a plus sign over here, then I'm undoing the fact that this component is towards the center. So I want the magnitude of the force, so it would be the Coulomb's constant, which is a positive number, times the magnitude of this charge times the magnitude of this charge. So I'm not going to put the minus sign in there, right? Divided by E squared, and this is mv squared divided by r. So I get k E squared over r squared equals mv squared divided by r. And at this point, I guess we can do a couple of things. I can, for example, cancel the, I can cancel one of the r's, and I can see that that v, it will be what? It will be the square root of k e squared over r, right? Or I can write it, do the canceling, k e squared over r, and this is mv squared, right?
Did you forget an m over there? On the one above?
M over there, right?
Yeah.
Thank you. Or I can just cancel the r's, and then notice that I have an mv squared. What if I divide both sides of this equation by 2? If I do that, then this here is a kinetic energy term, right? 1/2 mv squared is kinetic energy. So the kinetic energy of the electron can be written as it orbits around the proton, can be written as Coulomb's constant times the charge of the electron squared, or the charge of the proton squared, divided by 2r. Right, so that's one thing. So this is the first thing, and we get this result. That's like equation number 1, if you like. The next thing that Niels Bohr did is he wrote the expression for the energy of the electron, which would be the kinetic energy plus the electrical potential energy. So that's electrical potential energy. Going back to this problem over here, Newton wrote that the gravitational potential energy between these two objects, does anyone remember what the gravitational potential energy is? We have an object of mass m1, another one of mass m2.
The gm1 m2 divided by r.
Right? With a minus sign, -1 divided by r. Well, Coulomb wrote that the electric potential energy is Coulomb's constant, and then times the charge of one of them, which is plus E, times the charge of the other one, which is minus E, divided by r. So it turns out to be minus k E squared divided by r. This is the electrical potential energy. The thing is that in the case of the masses, right, if m1 is not the same as m2, you gotta keep them separate. But the charge of the proton and the charge of the electron are identical except for the minus sign, so that's why you get a minus sign, because one of those charges is negative, the other one is positive, and you're multiplying them, and you get an E squared because the magnitudes of the charges are the same. So this is the total energy of the electron as it orbits around the stationary proton. So the total energy E is 1/2 mv squared plus that electrical potential energy, which is minus k E squared divided by r. Yes? We good? I wrote a little small over here, I'm sorry. So the electrical potential energy is Coulomb's constant times one charge times the other charge divided by r, right? In the same form as that. So it's Coulomb's constant, the charge of the proton is plus E, the charge of the electron is minus E, and then divided by r. So this is just minus k E squared by r, okay? So you learn about this in Physics 280, so I'm just gonna use that result. You don't need to know that. So that's this. Now, notice that I can write the kinetic energy term, the 1/2 mv squared, as k E squared over 2r, right? So I can take this so that the total energy is k E squared over 2r minus k E squared over r. So the total energy of the electron is minus k E squared over 2r. And the fact that the energy is negative means that the electron is bound to orbit around the proton. It's very similar if you consider an object orbiting around another object, M1 and M2, and you get a very, very similar expression for the mechanical energy. In that case, it's called mechanical energy, kinetic plus gravitational potential energy. But in this case, it's just the energy. It's kinetic energy plus electrical potential energy. So we have that. This is like equation number 2, if you like. Okay? We have that equation. We have equation number 1. All of this is stuff that people knew, like if they were asked. Okay, so think of the electron as going around in a circular orbit around the proton. Now, Niels Bohr's contribution came in the next step over here. He said that the orbital angular momentum of the electron as it orbits around the proton right? About the proton is equal to a number, and this was like a trial and error type of thing that he got to this point. I guess he was trying different things, and then he happened to try something that led to a very good result. So it was a number multiplied by h bar, where two things. H bar is shorthand notation for h over 2 pi. Planck's constant divided by 2 pi. I guess it shows up a lot that people got lazy, and instead of writing h over 2 pi, h over 2 pi, h over 2 pi, they just called it h with a bar across. It's just defined as Planck's constant divided by 2 pi, because that shows up a lot. And but that's not something that, I don't think Niels Bohr introduced that, but he introduced this here. And what he said was that n, so that, he was able to choose the values of n that he could combine with these equations to then predict what the energies emitted from unexcited hydrogen atoms would be. And, in order for his theory to match experimental data, he said n can only be 1, 2, 3, 4, a positive integer, not 0, but 1, 2, 3, 4. And n is known as a principal quantum number. So n is called the principal. At that time, it was just called a quantum number. But it turns out that with quantum mechanics, there are other quantum numbers that show up. So this is the principal one. It's the principal quantum number, n. So we have equation number 3 here. Equation number 3, equation number 2, equation number 1. Okay? And now we just do algebra. Can we express the total energy in terms of constants and n? And by the way, the orbital angular momentum is also m, right? If this is moving in a circular path, right? The orbital angular momentum is m, the mass of the electron, times the speed, times r. So, he wrote, I guess, let me make more room over here, mvr. So he says that this total orbital angular momentum, which is m, the mass of the electron, times the speed, times r, is equal to that. And this was a matter of serendipity, just luck, but it worked, right? And so, okay, so I'm going to erase this here so I can do this algebra. Okay, so what if I take equation number 3 and we write mvr is nh bar, and I solve for I need an r over here. I have this other expression over here. I guess it doesn't really matter. Suppose I solve for v. So v will be nh bar over mr, correct? And then if I take this expression from here, right? So this expression, V equals the square root of Coulomb's constant E squared over mr, right? If I take that, becomes, if I take this and I plug it in here, then I'm gonna get what? I'm gonna get NH bar over mr equals K E squared over mr square root. Is that right? And if I square both sides, I want to combine the r's. If I square both sides, I get n squared, h bar squared, m squared, r squared equals, and then on that side it will be just k e squared over m r. Right? And if I cancel one of the r's, I get that r equals n squared h bar squared over k, and then one of the m's will cancel, right? K e squared, and then I have an m downstairs, right? Is that right?
I think so.
So I'm going to write down that expression over here. This is the distance r is n h bar over k m e squared, right? So that's one equation. All right, and with this equation, the energy equation, which is minus k e squared over 2r, becomes, now what I'm going to do is I'm going to take this expression and I'm going to plug it in here for r. So that the energy equation becomes minus k e squared over 2, and then that r is going to go in here, which is n squared h bar squared over k e squared m. So the energy becomes minus, all right, I have a k and a k, so that will be k squared, e squared, that's e to the fourth, and there's an m in there that goes upstairs, right? Minus, and then there's a 2, there's an h bar squared, and then there's a 1 over n squared, right? Yes? Now, we know the values of these parameters, right? So, the mass of the electron is 9.11 times 10 to the minus 31 kilograms. Coulomb's constant is 9 times 10 to the 9th. Newtons meters squared over kilograms squared. Planck's constant is 6, what is it, 6.34 times 10 to, no, 6.6 times 10 to minus 34? I don't remember. 6.67 times 10 to minus 34?
I thought it was 6.626 times 10 to the negative 34.
Could be. I just don't remember. 10 to minus 34, I think, right? But 6 point, let me look it up. Or in the book, Alan, you have it in the back. Maybe by one of the homework problems here it'll come up.
6.626.
6.626, good. 6.626, okay. Times 10 to the minus 34, right?
Yep.
All right, so this will be in joules second. Anything else? Let's see, we have, oh, and E is 1.6, probably O2 times 10 to the minus 19 coulombs. Is that 1.602? Electric charge? Oh, well, somehow. That rings a bell, but anyway, 1.6 times 10 to the minus 19 coulombs. Okay, so let's do this then. So the energy of the electron will be minus, and then we have this bunch of numbers here. 9.11, this is good to do once in your life, times 10 to the minus 31. Coulomb's constant is 9 times 10 to the 9th squared. The electron charge is 1.6 times 10 to the minus 19, and we have to raise that to the 4th power, divided by 2, and h bar is h over 2 pi, right? So that would be, so I guess h bar is h over 2 pi, and this is 6.626 times 10 to the minus 34 divided by 2 pi. I think this is like 1.05, somehow that rings a bell, times 10 to the minus 34. How much is that? So I'll just write this, somehow 1.05 rings a bell, we'll see, check, because I may not remember well, and that's squared, and this is 1 over n squared. Is this right? 1.05? Or is it 1.35? I don't remember. How much is 6.626 divided by 2 pi?
1.05.
1.5? Okay, so we're good with that then. Okay, so what do you get for the energy levels over here? Minus, and I notice that I use everything in the metric system, so this is going to be in joules. It's going to be some energy in joules, 1 over n squared. And I think you get a pretty small number, maybe 10 to the minus 18 joules. I don't know, tell me what you get.
I got 2.19 times 10 to 18 minus 18. So 2.19.
2.19, 2.19
Yeah. And then
times 10 to the
minus 18.
minus 18 joules. Okay, so that's very small joules. So let's convert this to electron-volts. 1 electron volt, it's another unit of energy. It's 1.6 times 10 to the minus 19 joules. So the joules will cancel, and we'll have this in electron volts. So the joules will cancel, and we're gonna get this energy as minus 1, and then n squared, and this will be in electron volts. And you should get 13.6, but I want you to double check for me. Do you get 13.6?
13.68, yeah.
Okay, so we're off. 13.6 is what you get. If you use the more accurate numbers. Like that's probably a 6.02, but anyway, so we'll just use that. So notice, according to Niels Bohr, the energy of the electron only depends on the value of n, where n is either 1 or 2 or 3 or 4 or 17 or 27 or 1,000 or 357, a positive integer, right? So this expression over here, this is oftentimes written as the total energy, and then you use n as a subscript because the value of the energy will depend on what value of n you use, right? So where n equals 1, 2, 3, 4, blah, 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 a positive integer. Now, a few corrections. The orbit of the electron around the proton is not necessarily circular, more elliptical. But that's one thing. Number two, so that's one thing. Number two, this expression turns out to be wrong. This expression turns out to be wrong. It's close, but it's wrong. In quantum mechanics, this gets replaced by the square root of L plus 1. It's another quantum number. So that's a correction. According to Niels Bohr, because n can only be 1, 2, 3, 4, according to his theory, the electron could only be in certain specific orbits, only at certain distances away from the nucleus. That's wrong. The electron can be anywhere around the nucleus. It can be anywhere. It's just that the most, the most, when the energy is a specific value, right? When the energy is one of these, this is the most probable position that the electron has, but it could be anywhere around the nucleus. Now, this expression turned out to be exact. So this is really his achievement over here. This expression turned out to be good. So there were some features about this equation that had to be fixed. The orbits are not necessarily circular. More generally, they are elliptical. The electron doesn't, according to Bohr's theory, the electron can only be at one distance away, or this other distance away, or this other distance, but never anything else. Well, that turns out to be wrong. It's just that when you calculate what's called the expectation value of the orbit, for a specific energy, you end up with that expression. But it's not that it has to be there all the time if the energy is one of these allowed values. But this was a success. This number over here, so let's think about what, these are called the Bohr orbits. Let's think about the values of R. So it would be n times, now h bar is 1.05 times 10 to the minus 34. And then you divide by Coulomb's constant, which is 9 times 10 to the 9th. Actually, if you look up Coulomb's constant, it's going to be 8.99 times 10 to the 9th. But, I'm just going to use 9 times 10 to the 9th. The mass of the electron is 9.11 times 10 to the minus 31. And the charge of the electron is 1.6. Somehow O2 rings a bell, times 10 to the minus 19, and that one gets squared. And that's going to be a distance in meters. So this is n times, some number in meters. So could you do that for me, please? Let's see what you get. Where?
Over there.
And h bar squared, yes, k e squared m. Oh, only here, right? Oh,
Oh, and
k.
squared.
N should be squared.
Oh, n squared, yes. And I would have, that's something that I would have figured out. But after I made a mistake. Yes, only because I remember the values. Thank you. Good. So this should be squared, right? Then km is squared. Thank you. So what do we get? You can imagine they had no calculators back then in the 1913 or so. Those people were good at taking square roots and cube roots. They became very good at that. So I'm doing this math over here, this algebra, really what it is. But then I want to focus on the results. I want to talk about the physics of the results. Okay, but this is good to do once. Anyone get a number for that distance over here in meters?
We just
How about 0.529 times 10 to the minus 10?
I got 5.25 times 10 to the minus 11.
Yeah,
It's about the
so
same.
thing.
Yeah.
So
I
0.5,
was like, I can't math.
29? 0.5 what?
2.5.
25. Okay, let's make it 3.
Oh.
Times 10 to the minus 10. Okay, there is one unit that's, I don't know, people don't use that anymore. Have you heard of the angstrom? It's 1 and then it's like, the symbol is like that, like 1A. So this is defined as 10 to the minus 10 meters. So if we convert this to angstroms, the meters cancel and the 10 to the minus 10 cancel, and you get that Rn equals half an angstrom, is what I remember. Times n squared. So, this was a Bohr, 1913, and this was Bohr. He was given the Nobel Prize for this work. Although some features were wrong, but he still managed to get the correct expression for the energy balance. So now I like to erase all of that algebra and just talk about the results.